Hey y'all, just want to close up 8.5, which is rotational dynamics, and emphasize a little bit on torque. Let me kind of just share some things, and I'll get it up on the whiteboard. We were trying to make a correlation with force equals mass times acceleration. I wish they would have said the sum of the forces, or the net force, because if I apply a net force to an object, right, and it begins to move, there is acceleration, and it's proportional or inversely proportional how much mass there is. There is a rotational equivalent, and that's called torque. Now, torque is a radius, or a force applied at a certain distance from the axis of rotation. So force times that radius from the axis of rotation. We did some fancy substitution, right, mr alpha in for force, okay. We get mr squared alpha. Now that mr squared is representing what we call the moment of inertia, or rotational inertia. Now inertia is that resistance to change, right? So objects of different shapes, right, and different quantities of mass, and different locations related to its radius or distance from its axis of rotation impacts how easy or difficult it is to start rotation and or stop rotation, okay? So I want to just give a little background on our last discussion board about that moment of inertia, and then it's going to correlate to what we're doing today as far as ranking items. Ultimately, while you've got this mr squared, it really is technically the sum of all the mr squareds, okay? The sum of all the mr squareds, and they replace that mr squared, or the sum of all the mr squareds, with I for inertia. So the net torque is equal to I alpha, okay? So what I'd like to do is put this up on the screen and then give you that connection to what we made, or try to make a connection with your ranking tasks. So we have just that correlation. Sum of forces, mass times acceleration rotationally, and this could go on your summary sheet. Sum of the torques is equal to I, right, rotational inertia, times alpha. So if I apply a torque to a rotating object, I'm going to get a net, or I'm going to get a rotational acceleration. So the link is pretty tight. Again, on that summary sheet, you can put that down. But I basically was the sum of all the mr squareds. And I was hoping we'd pick that up. But when we had that axis of rotation, and you had like different masses, let's see, and then maybe I put one here. Now this isn't an example from the sheet, but it's good enough. If these are all the same mass, and then I have these units of distance away. So this is, I guess they just drew a grid. And this is my axis of rotation. Okay. What would my net or total rotational inertia be for this object? Okay. Now, just because it's this way doesn't mean it's a negative or it counteracts the rotational inertia. We're still trying to move this around the axis of rotation. So this one would be the mass, and then it would be 1 squared, right? And then I've got 3 of these that have that mass, but they're also at 1 squared away. And so when we get into that final one, I've got 2 distances away, but there's only one of them, m, and 2 squared away. So ultimately, even though I don't know my mass, but they are equivalent, I've got 1m, I've got 3m, so 4m here, and then I've got another 4m, so I have a total of 8m as far as my rotational inertia. So really, you could calculate this for each one of those tasks, or each one of those items, and figure out which one had the highest. And I'm going to pause the video, and I'm going to go find my solution. I transferred from my parents' house to my house because I needed internet. Now I've got internet, so I get to work from home now, which is kind of nice, so I don't have to go back and forth and whenever Schoology goes down, I can clean stuff in my house and get stuff done. So let me pause and get the answers from our discussion board yesterday. All right, I'm back. So my solutions, and hope this works as far as the part of the screen. I had D first. It had 37M associated with it. Then A had 24M. E, right, 16M. B had 13M. And C, 12M. And finally F with 6M. So for all those that made their predictions and made their comments and said we match, but we're not quite lined up, take a look at that sheet again and see if we correlate. Now, I could have done something wrong. Okay, I get that, right? I do that. And you guys catch me, right? Which is great. You're listening. So this is my ranking order. Why don't you check that, see if you got the same thing. And yeah, I want you to watch the Walter Lewin video. That's the extension. You are going to use this principle, and you're going to think about this principle about individual masses and how they relate to objects rotating. So something like this, or disk. Ah, that's a really bad disk. Or a sphere, right? Oh, I used to be able to draw a sphere. Maybe it's the whiteboard, okay? Where you've got the sphere itself. I probably should use my shading techniques. And how they rotate about an axis. And how does this, right? How does this item, as far as mass and its distance away from this axis rotation, give us input into different types of shapes? So you have 5 shapes to rank, and they are on that discussion board. And then we'll get into some explanation about how his demonstration works. And I'll post that video on Friday. I hope you guys are well. I hope you enjoyed that weather a little bit and don't feel stuck at your computer. And pretty soon, we'll get another weekend. We got to get some good ideas on how to not make our normal day of doing work all the time different from our weekends. So I think that's our next challenge. See you guys later.